Um, I guess it's going to be lecture number 8, right? All right. Okay. So, well, we finished somehow approximation methods, right? Which including perturbation, right? Theory, and also, of course, of WKB, right? And today we're going to look at another approach to solve the quantum of the wave function. Okay, part. Well, which is this guy, actually. Yeah, I think it should be. Is it right? Yeah. But well, we have to include Dirac as well, because Dirac, who is the one firstly pioneer to explore the connection, right? Explore. I would say a connection between Lagrangian mechanics and quantization. Okay. All right. And then he did, well, I would say he haven't succeeded that kind of fully successed, but he laid some foundation, and then later on, Feynman took his idea to develop further, and then finally he gets what we call now part integration. Okay, let's briefly first. Again, suppose I'm going to use this Dirac notation symbol, right? This is belong to the Hilbert space, right? I'm not going to explain to you what is the Hilbert space. I suppose that you learned about this thing from the previous term, right? In the previous course on standard mechanics, right? And so, which is you could this wave function has to satisfy this Schrödinger equation, right? This is the Hamiltonian operator. Okay, with this normalization condition. Okay. All right. So it's quite a bit, not a bit, but very useful to use this kind of Dirac notation, because we just ignore the coordinate of, of the wave function, right? It's kind of coordinate dependent somehow. Not really, but actually you don't need to do the integration. That you don't need to put the integration like that. Something like, well, that kind of make things a bit difficult. Okay, so next we're going to look at the time evolution, which is I give you as a homework, I believe, that to prove that actually if you have this kind of operator that actually map this state further a bit, right? If you have a line, right? And then this is t, and then this is t plus delta t, right? And then on this, suppose this is my Hilbert space. Suppose, well, but okay. So let's put in this way, because I prefer to use the hypersphere, because suppose that this is a point that actually this one, and this is actually live on the surface of this sphere, which at time t, delta t. Okay, and then so you have a map, actually map to this point and map right here, right? Actually, you can think this is a map, and then, well, we demand that during the evolution that actually taking place on this surface of this, I mean, the norm of this has to be satisfy that condition. And so here you can do the Taylor expansion, right? I believe that you did this before. We keep only the first term in the expansion. Then, so you're going to have this one. Okay. And you can, of course, you can apply at this point equation. After you apply, then you will get this equation, right? And the limit, suppose that this delta t is extremely small, right? This, I mean, this quantity, I mean, can be turned to be this right here. Actually, this is very trivial, because if you do the Taylor expansion, right, and then you keep only the first order of the delta t, and then actually there is infinite term of it, but since your delta t is very small, then you keep only first two term, then that is going to be nothing but the exponential of this function. Okay? Right, okay. So, well, and of course that this new, I mean, have to satisfy this property, right? Because what I did impose that, suppose this is, note that this is a cartoon, okay, cartoon version of time evolution of this. Okay, don't take this as some thing but this is might be a way that we could represent thing. Okay. Yes, of course, you can think that this sphere is your Hilbert space somehow. All right, so with this, it means that I can take this right here. So it means that, so it demands that actually this, the term in the middle must be satisfied this condition, right? And we know this is a unitary condition, and that is the reason why the time evolution operator then your is a unitary operator. Okay? I mean, what is meant by unitary preserving norm, right, of during the process. Okay? Otherwise, then you will get what you don't want, right? Because you need to make sure your wave functions satisfy the normalization all the time, right? Okay, are we good here? Okay, so this is only just few steps, very tiny step on this. If you think this is going to be your delta t, right? Then it means that, so I can, of course, we can compute plus 2 delta t, right, by apply another u, right, with the first one, which is this one, right here. Then you get 2 delta t here. What does it mean? It means that if you keep doing this, n minus 1, I believe it should be 2, n, I suppose it should be n, then it means that you need to do this n times, right? And so it can be put into this delta n here. No, to the power n, right? Which is equivalent with this one here. And so if you look at, I mean, this t, this should be n, okay, suppose this should be t, T1 and T2. All right. And this T2 minus T1 divided by n equal delta T. Okay. Suppose that you do the time slicing in this way. So, and each of the block come with the width delta T, and then you have n of it, right? You have this, and so then what you have is T2, T1, right? Here, all right. Okay, so on the top axis, so you have T1 and T2 here. It means then you could map here somehow by this operator U. Well, yeah, you can think of this U map, but actually on the sphere, hypersphere, I would say. T1. T2. Okay, this again. This again, which is preserving the norm. Okay. Hilbert space. Okay. All right. Then it means that your wave function at later time can be mapped by using this unitary operator or the time revolution operator. Oh shit. Okay, sorry about that. So next, we consider the wave function on space X, okay? Then what I did is I'm going to take this X2, okay? I just take the ket, right, of the X2 from the left-hand side, right? But here, this bracket, I mean this ket, no, this is the bra, right? Sorry, this is a ket. You need to insert somehow. X1, right? To match the position with the time right here. Okay, so it means now you can pull out the integration. you have now I define this new object, right? So where x going to be right in the standard showing the presentation, okay? And then here we come to this object. So now we define a propagator, which is normally people use this kind of symbol K. Okay, this is going to be our propagator. Then this equation can be put into in terms of the propagator, right? This, okay. Up to this point, equation. Is it too quick for you to catch up? All right, okay, good. Okay, then. We also know that this, sorry. Suppose I change my my label a little bit to be n and not, right? Here, x2 is going to replace to make thing consistency. No, to make thing that to be what I want. Okay, so of course this can be factorized, right? Because look at this. So this n and this u, right? Not right here. And do you know that actually your u can be factorized? You can split the u into this. So with this condition, right? And so again, I can do insert this completeness okay, here into the middle. Then I pull out the integration. So what I have is here, right? Are we good here, up to here? Okay, so it means that what we have your propagator here can be factorized, or it can be split right here. Okay, like this. Okay, this is known. This whole process factorization. Okay, or it can be split. Okay, so if we look at the diagram, suppose this is the t x and t, the diagram here, and suppose this is the point that we call x0, and this is the point x1, right? You x0, t0. Oh, no. X, so t0, tn. No, this is xn, sorry. I just confused myself. Actually, I change all the symbol, my notation already, okay? So, because this condition t, it could be anywhere between Tn and T0. If I pick T1 at this point, I'm going to have a line that runs through this point T from plus infinity to minus infinity right here. This is the reason why we have to integrate this point from minus to plus infinity. It means that you're going to have a path that connects here, or you have this, or you have that, or you have that. You have, well, infinite way. So, infinite way. Right. To make a connection between x0, between this point, these 2 points. So from this diagram, this is kind of makes sense. Now, this is the reason why you have to do the integration, all the possible points, right, at this particular time t1, right? Because you can make any connection between this point and this point throughout this line, because the point on this line is infinite, right? That is the reason why we have this kind of integration here. Is that okay for you? All right. Good. And then, at the moment we focus on the math first, and then later I'm going to give you the physical meaning later. What is the meaning of the propagator? Is that okay? And you, of course, that you can keep doing this process. Keep doing the factorization. Right. So if you do that, I'm going to skip. But if you do that, you're going to have this kind of symbol. Okay, so you're going to, whoops, sorry. You're going to have this thing. With the condition, actually, this is the sorry to mess up this two lines together. So again, if we draw a picture with this, this is going to be x, and then this will be t. So suppose this is the same point. I mean x0 and t0, and this is xn, tn. So it means that you're going to have a bunch of this line right here. You have to be good at drawing here to learn physics, right? And so in the middle, we just leave it because we know what's going on in the middle. So it means that so you could have a path actually go something like this, and then up here, right? Or like this. Or like this. Well, there is infinite way that you can draw a graph, but I will draw some of it. Okay, this kind of thing. But actually, you have the infinite of them again. Infinite of this kind of graph that you can draw, but we just stop here because we need to move on. If you get the point, then that's not a problem. Okay. Up to this point, now we're going to look at this object. Next, we consider this object. Okay. This object is just a tiny bit between these two lines, right? The propagator that actually you consider the connection between these two, any pair, right, of this of the lines that you partition your space. Okay, so this, of course, can be put here, right? So where delta t, okay? Are we good here? And of course, you can turn your U operator to be this exponential function, right? Like this. Okay. Which is actually okay, this one. Okay, so note that if you have any function of the operator that acting on the function, okay, so you will get that this kind of thing. This is eigenvalue, right, in this way. So we need this formulation. So which is, I'm not going to prove it for you. I believe that you understand how to prove it. It's not difficult. Maybe it's difficult, but yeah, just take it for granted at the moment. We have that. And also, if we have, if you look at the formula, I mean the last line that that I put on, look at this. So this is the operator that's actually acting on the space. This is the space function, right? But this t actually is a function of momentum, which is nothing to do with this. I mean x. So what we can do is that okay, next we also need this okay, delta t, delta t, delta t. Since it's very small, yep. Oh yes, of course. Thank you. So you need this splitting. Splitting. You know that this, what kind of formula that we use to split this kind of operator? Baker-Hausdorff, right? Okay, yes. You know that, and I'm not going to prove that for you. I just use it. Okay. Once you have that, so the propagator that we're looking is going to take the form okay, this one. And now, since this operator can act on this state, right, and it's going to give you just a numerical value, right? Then it leaves you only this t operator inside the bracket, and then you can take this v out, right, here. Now this x, look at this x is turned to be xj, all right, already, because after you take you use the eigenvalue that I put there. Okay, you can take it out. Then now next you have to deal with this function. What you can do is that you can again you can insert the completeness relation for the p, right? Suppose that we choose pj. All right, here, something like this. So the question is that can we choose pj plus 1? So now, actually there is the 2 point, right? This point j and j plus 1. Now I say that I put the completeness relation of the p at point j. The question is that can I choose this completeness relation of the p at j plus 1? Is it, can we? No, why not? Why is that? No, you can, of course. We can choose. You can choose to work with this, but I'm going to leave it as a homework for you to prove that actually it's going to give you exactly the same at the end. But for the moment, I just choose this point, j. Okay, so it means that, so pj okay. So again, this one act to this point, right? Oh, sorry, there must be a potential term out there. So once this operator acting on the state, right, you will get. Oh, this should be plus 1. So here, up here, so you will get pj, delta t, pj, delta t. Okay? Up to this point, any question? Because you're acting on this pj, right? This inside this operator has to turn to be pj. Okay. So next, we use this kind of relation. Actually, I believe that you know how to get this kind of relation, right? This is kind of Fourier factor that you can turn from the X space to the P space, something like that. Okay, so you use this. And so, of course, and you apply this into above formula, right? So you will have square okay. Up there you get this thing, this term, is Pj squared over m. Okay, just a standard notion of the kinetic energy. Okay. Okay, so if you look at this is nothing but the Gaussian integration, right? This is Gaussian one. So you can do the integration explicitly. So it means that at the end, so what you have is that m. So I do recommend you to check all my calculation again to make sure that I don't miss anything or any factor along the way. But I hope that I do things right. And this is here is a discrete Lagrangian. Okay. This is okay. This is Lagrangian. Okay. Are we cool up to here? So now we recalling the propagator, this one. We should actually, after you do the integration, n over 2, and you have this product from xk. You have summation here, n minus 1, t, xj plus 1, xj. Yeah, this is delta t. Okay. Okay, are we good up to here? So now we consider the limit, which is n approach to infinity, which is very huge, and your delta t approach to 0. What does it mean by having these limits? What does it mean? Of course, yeah. Well, actually, okay. Let me draw you again a graph, roughly. So this is a 2-point, right? And then, okay, we may start with this kind of thing. All right, which is okay. Which is n. And the width delta t. And if you increasing, the part that you consider here. If you increase okay, and with delta t prime, which is smaller than delta t. It means that your path will look like this. It's going to be okay. And then if you take it again, now it's very, very close, very close. I mean, very here, very close, very close, very close. No, yes, of course that this is the one propagator. But what I try to make sure that you understand these limits is that, okay, you will see. Then let me draw it for you. Okay. This is very large. Okay. And your delta t here, very small. You see the difference between these three pictures? What is different between them? Of course, it's yes, of the scale. Anything else that you could notice? You could see the pattern of the part, right? It's getting smoother and smoother, right? Yeah, that is the point. Along this process, the part getting smoother and smoother. Okay, it means that, so if you start with this, it looks like the discrete thing, right? You could see some kind of the part that actually jiggling around, right? But once you take that limit, if you take this limit, you could imagine actually the part will go smoothly from this point to that point. All right, so let me draw here because make it close because I don't want to start over there. It's too far. So it means that if you take the limit, under the limit, so your part you get something to be like this. Okay? You will get a smooth part connect. Okay? Okay. Is that okay for you? All right. Cool. And then under the limit, this delta t, right, can be changed. Well, you could change this summation to be the integration, right? Right. So your propagator Okay, then the fancy I'm going to define later. But the exponential part, this bit turned out to be the integration with respect to the time. So the initial point would be t0, and you end up with the final point, which is actually tn, right? And this Lagrangian could be turned to be the standard Lagrangian, right? This, which is in this case, okay, the standard one, okay? Because this x dot, if you look at the discrete Lagrangian there, the x dot, you could think that actually x dot is xj. This is the definition of the x dot, right? That's what we have. Under the limit, so this turned out to be the derivative, right? Okay, and then next, the fancy D. This thing, and you okay? Are you sure? Okay, this limit to pi h bar okay, and square root n over 2. If I am not sure, I think it should be only square root n. I'm not sure. I think this should be only square root n. You have to check again yourself here, but I believe it should be only this one. Okay, this whole bit going to be embed. This whole bit going to be embed into this fancy D. All right. Okay, so we have arrived at the definition of the propagator, right? And then we look again at this. Suppose okay, at this formula here. So you could think that this thing could be transition amplitude. Right, that you could map your state, right, at the initial state to the final state through this this one. Okay. So it's going to, and this propagator has to satisfy the probability condition, because you need to you demand the normalization condition on this. So let's see what we could get. I need to keep that picture, and then I'm going to explain that. Let's have a look at the property. I try to make myself because I think I could not finish on time, and because a lot of things that I need to cover. Okay, look at, sorry about this, xn. Okay, you need to, okay, so can you try yourself first? What you could get from the right hand side? Can I take a 2-minute break to get some water? Okay. And then I continue. Okay, hello. Okay, so what do you get? 1, definitely. So if you don't get it, I'm going to leave it at homework for you. Of course, that you need, right? You need this to be true, right? It means that so it's demand something extra formulation for the propagator to make that condition fulfill, right? All right. I'm going to leave it for you as a homework to do it yourself. Okay. Right. Then, so suppose it means that so now we look at the physical meaning of it. Right. Suppose here, this point, you map this point again on your Hilbert space, right? Suppose this is the point, right? And then you do the map. Yeah, I should use this rule here, right? This map, right? And then you also have another point that xn, right? We should actually, you're doing a map here. So this formula here telling you that there is an infinite way on this space that you could move this object to map this object to this new point on this Hilbert space throughout this kind of trajectory, infinite of it. So I think, so you're going to have all possible paths, right? All possible paths here. And then it's still the same, but actually the norm of this wave function has to be p-step. But you have to keep in mind that actually there is, if actually there is the dual space of it, you have to invest, you know, the dual space, right? Because there must be another object which it represents, yeah. Where is n? Yeah, right. Okay, this kind of thing, the dual of it. But once you need to do the inner product, right? That condition, this condition, you need these two space to do. Yeah, one object coming from the one space, in another object come from another space. Something like that. Okay, so let we put here. Okay. Okay, this is the quantum version. What we have all of before this, we have a classical version, right? Which is, if you draw again, this is an initial point. And this is the final point. You have only one part, right? You have only one part. One true part, which is called a classical part. Right. And this is classical part satisfy this condition. I mean a critical condition of the action, right, where the action defined as the integration of this Lagrangian, okay? All right. And of course that this, critical condition gives you, give you the Euler, right? Give you Euler-Lagrange equation subject to initial condition again. Okay? What I mean by subject to is mean if you move the initial condition, you will get different part. Okay, that is the thing. But here classical. So your classical particle will take only one part that actually you are, actually the action is critical. But in the quantum world, your particle doesn't care actually. They take all possible parts. In the quantum world, a particle take not only one, but all possible parts. Okay? This, but this is the difference. Okay? But you have to keep in mind that actually this, this part, the classical part is one of them. Okay? In this all possible way that your quantum particle can move from this point to that point, the classical part is okay, one of the choice. That okay. And under the limit, once you take H bar approach to 0, okay, that is called classical limit. Yeah, right. The part that actually are not the classical part will be interfere destructively, and then leave you only one true part. Okay, so what happened here is that, so I'm not going to prove it for you, but you can read from my book actually. But I'm going to give you as a homework to get some idea about how to take the classical limit here. So what happened is here, all non-classical part will interfere destructively, right? Okay, leaving only part around the classical one. The part around the classical one, which is interference constructively. Okay, มันเสริมกันผ่านใกล้ๆกับ classical part นะครับมันจะเสริมกันคือ okay, so let me draw this for you. So suppose there is a part that's really close to this, around this classical part right here. This kind of part that actually close to the classical part will give the phase term, right, constructively, and then but the part something like this is non-classical part, right? And then you could imagine that actually there is a part actually around this also, right? Around this part also. And then the fade factor will change rapidly, give us destructive pattern, and then it just vanish if you take this limit. That is some kind of a way to explain things, but you can prove with the math also. That I'm going to leave you as a homework to look at that on. But I think it's better to look at the book. Not only my book, I mean any textbooks on this. There is an explanation on this. Okay, up to here, any question? Dun, 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 dun. We haven't finished yet, actually, because we just got the formula. Let me point out again. We have a very, very beautiful formula for this. Let me start here. So we have a very beautiful formula that we call the propagator. Okay, we have this formula right here. No, actually, sorry, this should be psi. Okay. We have this beautiful formula, and then we have kind of a way to explain things in this way, right? With this kind of propagator, you could think that this is nothing that the transition amplitude, right? Right. Give us somehow of dynamics point of view, right? This, but you know that this must satisfy the Schrodinger equation, right? So it means that if what is look like Schrodinger equation is this one, right? Is it right? Am I correct here? H bar? Oops, sorry. Is it correct? My Schrodinger equation? Sorry. Oh, it should be minus, right? I'm not sure. Okay, let me have a look. Oh, yes. Okay. So, if it's so, what I'm going to do is that I'm going to do the derivative with this, and then what you get. So this derivative have to do with this object, right here, because there is a Tn here. Okay. Oops. Okay, and then well, what I'm trying to give you to give you is that the Schrodinger version, the Schrodinger equation version of the propagator actually. Let me think how to do that. So after we did this, so we also could we need what we need actually. Actually, interesting. How could I get the Schrodinger? Let me see. I think there's nothing here actually. I haven't put. Let's think about this, and then after I finish it, we stop, and then we continue next week. On we need to further investigate more on this propagator, and then I'm going to give you example that actually this formulation give us precisely the same result with the Schrodinger approach. ใครก็ช่างสัตว์ขยันส่งมาสาดมาจริงๆ Let's think about it. So what I need is that this equation actually. Let's think about how to get this one. I kind of can you help me to get this? Yeah, maybe. I'm not sure. Okay, let's see how it works. So if you turn this and what then? And you mean this one? Well, we can come out and then, I mean, to check on the board, if you like. Right. Okay. Yes, of course. I see. Yes. Of course, because this is the same, right? Then this must be the same, and you pull out the common factor, you get, okay? Cool. Yes. Okay, good. That very good. Okay. Very good. Okay, so we get, you see that actually we have also the Schrodinger version of the propagator. Happy? Okay. Okay. Any question before I stop here? I think I stop here because if I go further, I think I cannot finish in time by noon. But next week we continue a bit on this topic, and then we're going to look at we're going to use this propagator to do like a perturbation again, to see whether is it get to give us the same as what we did from previously, right? In before I mean New Year break. Okay, if you have no question, I stop here. Thank you.